Welding and cutting with the aid of combustible gases is an established method. The equipment used is versatile and relatively inexpensive. We can use either acetylene or propane as fuel gas. Understandably, the energy content of the fuel gas has to be very high in order to melt the metal as quickly and efficiently as this. Here, an acetylene cylinder is exposed to fire and exploded, which goes to show the kind of forces we're dealing with. Safety, however, is very good, and the risk of an accident occurring is minute, provided we proceed correctly and use proper equipment. On its own, a fuel gas such as acetylene or propane will not generate sufficiently high temperatures. For this reason, we add oxygen to the gas in order to raise the temperature of the flame. Let's begin by taking a closer look at the fuel gas acetylene. The behavior of acetylene varies considerably depending upon the pressure and mixture of air or oxygen. Acetylene consists of carbon and hydrogen. An acetylene molecule contains a considerable amount of energy. This balloon is filled with pure acetylene gas at a pressure of about 1 bar. It also contains a heating filament. When the acetylene molecules come into contact with the filament and are heated to above 300 degrees, they begin to break up into their constituent parts, carbon and hydrogen. We note the formation of carbon. The process is undramatic, and the acetylene gas neither catches fire nor explodes since it doesn't come into contact with air. Like the balloon, this hose also contains pure acetylene, but at twice the previous pressure, or 2 bar. We switch on the heating filament. And this time we get a powerful explosion. When we increase the pressure, the acetylene molecules are forced closer together. They're now packed so tightly together that when we add heat, they start to decompose. The energy thus released causes adjacent molecules also to decompose in a chain reaction. We call this acetylene decomposition. For this reason, we must never allow the operating pressure to exceed 1.5 bar. The higher the pressure, that is, the closer the molecules are packed, the greater the risk of decomposition. How then is it possible to store acetylene in a gas cylinder at a pressure of 17 bar? Since we know that acetylene cannot be compressed the way other gases can, we use a special type of cylinder, which contains a porous mass infused with acetone, into which the acetylene is dissolved under pressure. Acetylene decomposition can, however, be initiated by heating the cylinder to above 300 degrees Celsius. A flame accidentally directed at the cylinder may be enough to initiate decomposition. Once decomposition has started, the process cannot be terminated by removing the flame. It will continue inside the cylinder for as long as the valve remains open and the supply of acetylene continues. Closing the cylinder valve may arrest a limited decomposition. The hydrogen thus generated keeps fresh acetylene from reaching the decomposition zone. If a flashback arrestor is not being used and a flashback reaches the acetylene cylinder, this too may initiate decomposition. Flashback will be dealt with more extensively later on in the program. Up till now, we have concerned ourselves exclusively with pure acetylene. But how does acetylene behave when mixed with air or oxygen? When we burn a hole in the balloon and the acetylene comes into contact with air, we get combustion. Pure acetylene in air burns at a temperature of 2,300 degrees Celsius. When we mix the acetylene with oxygen for welding and cutting purposes, we raise the combustion temperature to 3,100 degrees. When mixed with air or pure oxygen, acetylene becomes explosive. We must therefore be on our guard against acetylene leakage. All it takes is a few % of acetylene in air to create an explosive mixture. One advantage of acetylene is its distinctive odor, which serves as a warning in case of leakage. The engine room of this Swedish mine-laying craft bears witness to the explosive force of mixed gas. The vessel was in the shipyard for repairs when one of the welders by mistake opened the wrong gas outlet, releasing a flow of acetylene and oxygen. As the hoses were not connected to the torch, the engine room was quickly filled with an explosive gas mixture. The gas mixture was ignited by a welding spark and exploded. Luckily, no one was in close vicinity of the explosion. Acetylene gas as such is safe. If we prevent leakages and do not expose the cylinder to heat or flashback, we eliminate the risk of acetylene decomposition and explosion. Propane also has a distinctive odor, but differs from acetylene in some respects. Propane is heavier than air and is thus prone to settle into pockets and confined spaces. Like acetylene, it becomes explosive when only a few % of it is mixed with air. Pure propane in air burns at a temperature of 1,900 degrees Celsius. When we mix propane with oxygen, we raise the combustion temperature to 2,800 degrees. Propane is stored in liquid form in the cylinder at a pressure of 9 bar. A propane cylinder differs from an acetylene cylinder in that it is provided with a safety valve that is activated should the pressure increase, as in a fire. Keep in mind that in order for the safety valve to work properly, the cylinder must be kept upright. Otherwise, the valve will be submerged in liquid gas. Oxygen is used for raising the temperature of the flame regardless of the choice of fuel gas. Oxygen is odorless and is perhaps best known for its uses in medical contexts. This may lead us to think that there are no risks involved in using oxygen, but this is not the case. The ambient air contains 21% by volume of oxygen. Oxygen plays an active part in all forms of combustion. If we increase the oxygen content by 3 percentage points to 24%, the combustion velocity will double. At 40%, the combustion velocity has increased tenfold. In pure oxygen, everything burns, be it steel or human skin. The risks involved were dramatically demonstrated when on January 28, 1967, 3 U.S. astronauts, Grissom, White, and Chaffee, lost their lives in an accident. The atmosphere inside the Apollo-Saturn space capsule was pure oxygen. One spark was all it took to turn it into a blazing inferno. Everything caught fire. Blow cleaning working clothes with pure oxygen is just as dangerous. One spark, and you and your clothes will burn until all the oxygen is consumed. Leaking equipment may cause the oxygen level in the surrounding air to quickly exceed the safety limits. Checking for leaks is a vital precaution. We'll return to how this is done later on. Using too large a nozzle in a confined space may also cause the oxygen level to rise quickly. You can avoid this risk by choosing the appropriate nozzle for the workpiece in question. Consult the cutting tables. Pressurized oxygen can cause metal and grease or oil to ignite. Never lubricate any of the welding equipment. and make sure that no grease or oil inadvertently comes into contact with the equipment. In the cylinder, oxygen is compressed to a pressure of up to 200 bar. If we were to chop the top off the cylinder, it would take 2 fully loaded tanker trucks, or 65 tons, to withstand the pressure inside. Although the oxygen is not in itself explosive, the pressure inside the cylinder is so high that if the valve were knocked off it, it would go off like a rocket straight through the wall or the ceiling. Believe it or not, this has happened on several occasions. A common feature of all gas cylinders is that they must be handled with care. Most importantly, the cylinders have to be properly secured, in use as well as during transport. What other precautions must be taken when transporting gas cylinders? All transportation and distribution by the gas company is governed by stringent regulations. The question is what we must keep in mind if we wish to transport gas cylinders ourselves. Gas must never be transported without first making sure that all of the cylinders are provided with protective caps. More recent models of cylinders feature protective caps, which are never removed. In a vehicle, even a slight leak may prove disastrous. For this reason, gas cylinders should never be transported in private cars or other covered vehicles. Use a pickup truck or an open trailer instead, making sure that the cylinders are properly secured, as in this example, against falling over or rolling about. Special rules apply to vehicles which are used professionally to carry welding equipment. The space used for carrying the cylinders must be well ventilated and clearly separated from the driver's compartment. Don't forget the enormous explosive power of acetylene when mixed with air. If exposed to fire, the cylinders may explode. Therefore, make sure that your cylinders can be easily removed in case of fire. Plan for an exit route and make sure it's kept clear at all times. In case of fire, inform the fire brigade immediately if any gas cylinders remain on the premises, stating where they're located and which type of gas they contain. Whatever you do, don't forget to use warning signs. To the firemen, they may mean the difference between life and death. We've now learned something about the gases we use. Now it's time for a closer look at the equipment itself. If we're to attain a high level of safety, it's essential we use equipment of the highest quality. Equally important is the care with which we assemble and check it. The equipment we use consists of gas cylinders, regulators, flashback arresters, hoses with mounted check valves, and torches to which are fitted the welding or cutting attachments. First, we're going to show you the correct way to assemble the cutting and welding unit. For the sake of simplicity, we'll confine our discussion to only one fuel gas, acetylene, from this point on. We begin with the cylinders. Make sure they're properly secured and cannot topple over. Never begin assembly unless you're 100% sure which gas the cylinders contain. Don't forget that the markings and the colors on the cylinders vary from country to country. We have to be sure that there are no dirt particles in the cylinder valves. We blow the oxygen valve clean. Always stand behind the valve and blow towards an open space. For acetylene, that is a flammable gas, we do a visual inspection of the valve. Make sure that the threads on the cylinders and the regulators are undamaged and that the gaskets are intact. Remember, the gaskets have to be changed each time the equipment has been dismantled. We'll now fit the regulators. Note that oxygen and acetylene have different regulators. In order to avoid a mix-up, these are provided with internal and external threads, respectively. Next in line is our first safety device, a flashback arrestor. One each for the oxygen and acetylene hoses. We'll talk more about how they work and what they protect us against later on. Since the flashback arrestors are not the same for the acetylene and oxygen, they're provided with different threadings, just like the regulators. We only use approved hoses that meet certain safety requirements. Hoses for the different gases must not be confused and are therefore different colors. First, we make sure that the proper hose clamps are fitted and that the hoses show no signs of cracking or other damages. We then attach the hoses to the flashback arrestors. If possible, do not use lengthening sections. If you must, use only approved hose couplings made of brass. Under no circumstances, use couplings made of copper or silver solder in combination with acetylene, as the ensuing reaction may cause an explosion. The hoses are fitted with check valves or flame arrestors in order to prevent gas from flowing in the wrong direction. As before, the connections for the acetylene and oxygen hoses have different threadings, clockwise and counterclockwise respectively. A precondition is that the connections are properly fitted to the hoses. Unlike the oxygen connection, the one for the acetylene is provided with a notch. All the couplings are tightened with a box wrench. Before fitting the welding or cutting attachment, we inspect the gasket carefully. The gasket won't last forever and has to be replaced at regular intervals. Altogether, worn or faulty gaskets have caused too many accidents. Finally, we place an approved fire glove within easy reach and make sure we have ready access to 2 fair-sized fire extinguishers. We'll now adjust the correct operating pressure. We begin by making sure that the throttle valves on the torch are closed. The purpose of the regulator is to reduce the high pressure inside the cylinders to a usable, stable working pressure. We check whether the pressure adjusting screws are in their outermost position, that is, that the operating pressure is 0. We then open the cylinder valves gently. Stand in this position when opening the valves. An important safety precaution is never to stand too close to the regulator. The dimension of the welding or cutting nozzle being used determines the correct operating pressure. Consult the tables. Turn the acetylene knob on the torch to fully open and adjust to desired operating pressure with the aid of the pressure gauge. Adjust the oxygen in the same manner. When using a cutting attachment, it's the pressure of the cutting oxygen which we adjust on the regulator. We must therefore open the cutting oxygen supply fully when making the adjustment. The flow of the heating oxygen is regulated by means of valves on the cutting attachment or the cutting torch. Remember that the operating pressure for acetylene must never exceed 1.5 bar. The acetylene pressure normally lies within the interval of 0.2 to 0.8 bar. In later models of regulators, higher adjustments are prevented by means of a safety valve, which is activated by excessive pressure. Although the pressure inside the cylinder drops as the gas is consumed, the regulator maintains the preset operating pressure. Up to the point where the regulator takes over, we have cylinder pressure. For a full cylinder of oxygen, this is all of 200 bar. We have learned that the cylinder valves should be opened gradually. The reason for this is that if we release the cylinder pressure too suddenly, we may get something called a diabatic compression. What happens is that the remaining gas is compressed rapidly, causing a sudden and considerable increase in the temperature. The combination of a high temperature and high pressure oxygen is then capable of igniting the metal in the regulator. If so, we're faced with a so-called metal fire. Leakage is a far more common cause of accidents than is generally supposed. Small leaks often cause serious damage when the gas is ignited. For instance, leaking gas from a torch or hose attachment can find its way into gloves and clothing and seriously injure the welder when it catches fire. We're now ready to test for leaks. We build up pressure in the system by opening the gas supply while keeping the valves on the torch closed. We use leakage spray. The hoses can be checked by submerging them in water. If a leak is discovered on the input side of the oxygen regulator, remember not to tighten the coupling until the cylinder valve has been closed and the pressure released. The friction in the threads together with the high pressure can start a fire. We're now ready to light the flame, but before we do so, we're going to take a closer look at the background to and the function of the safety devices we've fitted to our equipment. We normally speak of three phenomena: backfire, sustained backfire, and flashback. This is what a backfire sounds like. In this case, in a welding tip. The flame is either completely extinguished or extinguished and then relit again at the orifice of the nozzle. When the gas mixture burns faster than the speed at which it flows out of the nozzle, the flame drifts backward into the torch. We call this backfire. It's not a dangerous condition, but if it keeps up, we must stop welding or cutting and locate the cause. One common fault is that the control knobs on the torch are adjusted too low. Increase the setting and try again. The gas in the cylinders may be running out, or perhaps the hoses have become constricted at some point. The most likely cause, however, is a clogged or damaged nozzle. If it's simply a matter of clogging, then cleaning the nozzle will probably do the trick. If reaming needles are used, it's absolutely necessary to use the correct ones. If we increase the diameter of the orifice by using too large a reaming needle, the gas exit velocity is reduced, with backfire as a consequence. Chemical cleaning is a much gentler cleaning method. The nozzles are simply placed in a bath of cleaning fluid. 4 hours later, they're removed, clean and ready to be rinsed and blown dry. Another reverse reason for backfire is an increase in combustion rate, although the gas exit velocity is correct. This may happen if the nozzle becomes overheated. It occurs especially when welding in cramped spaces where the flame rebounds back to the nozzle or when cutting too close to the workpiece. The remedy is simple. Stop working and cool the nozzle in water. Backfire must under no circumstances be ignored. If you do so, there is a risk it will develop into a sustained backfire. The flame then reverses and continues to burn inside the nozzle or cutting attachment. You'll know when you got a sustained backfire since it gives off a whistling noise and the flame goes out. You've got 10 seconds to shut off the gas supply, first on the torch, then directly on the cylinder. Cool the torch in water and check the nozzle and the gasket. If we neglect to remedy a sustained backfire, this is what may happen. The attachment melts, and burning gas may burst out and injure the operator. This was a flashback with exploding hoses. It was caused by fuel gas and oxygen being inadvertently mixed before reaching the mixing point in the welding nozzle or the cutting attachment. We call this reverse gas flow. It can occur in the acetylene as well as in the oxygen hose. If worse comes to worse, the flashback will continue on through the regulator and into the cylinder. The causes may vary, but there are effective methods for preventing flashback. Reverse flow can be prevented by means of check valves. The check valve protects us against reverse gas flow. It won't stop flashback. The check valve is closed when the pressure on both sides is the same. When we turn on the gas, the valve opens. In the case of reverse flow, the check valve will close before the reversing gas reaches the hoses. Check valves are very reliable but don't last forever. For this reason, test the function from time to time. Although the primary task of the flashback arrestor is to prevent the occurrence of flashback, it also performs several other safety functions. The flashback arrestor has a built-in check valve which keeps the gas from flowing in the wrong direction. The flashback arrestor also contains a pressure-sensitive shutoff valve, which is activated by the shock wave from a flashback. Once it's been tripped, it must be reset. The flame filter in a flashback arrestor allows gas to pass, but not a flame. The filter extinguishes the flashback. In case of fire, the flashback arrestor is provided with a thermal gas shutoff, which is triggered at 95 centigrade. Since it's also possible for a gas mixture to enter the oxygen hose, it too must be provided with a flashback arrestor. It's vital that the flow of oxygen be arrested in case of fire. Another way to further improve safety is to use the torch-mounted flame arrestors whenever possible. In addition to being flame arrestors, they also serve as check valves and are capable of preventing hose explosions in case of flashback. The equipment we choose depends upon the rate of gas flow we require. With the normal gas flow, we use torch-mounted flame arrestors and a flashback arrestor at each of the regulators. With high gas flows, we use large capacity check valves and a flashback arrestor at each of the regulators. A very high gas flow requires check valves and twin flashback arrestors. But in this case, we normally use a high-capacity system as a central gas system, or cylinder bundles, not single cylinders. The purpose of the safety equipment is not to compensate for negligence in the handling of other equipment. The best guarantee we have for safety at work is our own caution. Make a point of always purging the hoses before lighting up. This removes any gas mixture present in the hoses. Purge one gas at a time. Since flashbacks always occur in connection with lighting the torch, it's only reasonable that we can eliminate certain risk already at this stage. One way is to always light the torch in the prescribed manner. It's important we understand the differences between an injector torch and an equal pressure torch. This is what a welding attachment for an injector torch looks like in cross-section. High-pressure oxygen flows at great speed through an injector duct, and in doing so creates negative pressure in the acetylene line. When the acetylene valve is then opened, the acetylene is drawn along into the mixing tubes and on out through the nozzle. The design is extremely reliable, provided we open the oxygen flow first and let the suction force in the duct establish itself before we turn on the acetylene. An equal pressure torch employs a different principle. Acetylene and oxygen are mixed at the same pressure. The mixing takes place either at this point in the welding insert or in the nozzle of the cutting attachment. If we turn on the oxygen first, there's a risk that the pressure will be too high. The oxygen will then drift backwards into the acetylene hose to make mixed gas. The preconditions will then exist for a flashback. When using an equal pressure torch, we therefore open and light the acetylene first. We then open the oxygen gradually until the flame tells us we've obtained the correct operating pressure. If a flashback occurs, shut off the acetylene and the oxygen immediately, using the valves on the cylinders. You now understand how important it is to always keep a fire glove within reach. Place your hands on the cylinder to see if it's warm. If it is, evacuate all personnel and rope off the area. Call the fire brigade. The cylinder must be cooled down for at least 24 hours. The risk of explosion is very great. If the cylinder has been exposed to fire, we must not attempt to check whether decomposition has begun. We cannot determine whether a cylinder is hot because of decomposition or because of the fire. Instead, evacuate all personnel and let the fire brigade take over. Personal safety equipment is important in welding and cutting, especially since we sometimes tend to forget that the high temperatures involved can cause very serious injury indeed. One danger is spatter. Without protective goggles, it can harm the eyes. This is what they should look like, with protection at the sides. We take it for granted that everyone wears welding gloves and flame-proof overalls when welding or cutting. Oxy-fuel processes generate fumes and gases to a greater or lesser extent. Examples of hazardous gases we must protect ourselves from are nitrogen oxides and carbon monoxide, especially in confined spaces. All welding in confined spaces is risky. Leaking fuel gas can quickly fill the space and ignite. Oxygen escaping from a leak or incorrectly dimensioned cutting nozzle can rapidly reach dangerous levels. We know for a fact that the flame derives 60% of its oxygen from the ambient air. In confined spaces, we may therefore fall prey to oxygen deficiency, which in turn may lead to unconsciousness. A basic rule when welding in a confined space is to provide for adequate ventilation. This eliminates most of the risks. Furthermore, you should always be accompanied by someone who can quickly shut off the gas supply in case of an emergency. The hot flame used in welding and cutting entails considerable fire risks. Every year, huge sums are lost because basic safety rules have been neglected. A major source of problems is welding sparks. Sparks and slag with a temperature of 1,000 degrees Celsius are capable of starting fires a considerable distance from the work site. Another common cause of fire is simply forgetting how hot the flame actually is. It's worth keeping in mind that at half a meter's distance from the tip of the flame, the temperature is 300 degrees Celsius, and that's hot enough to start a fire. It's often difficult to remove inflammable material from, say, a rounded pipe. Therefore, it may be tempting to take a chance. But the pipe could ignite adjacent material a considerable distance from the welding site. When cutting, there's a tendency to forget about the slag spatter on the reverse side of the plate. Without a welding guard in place, such neglect may have dire consequences. Many countries have legislation which makes it mandatory for a fire guard to be in attendance during all temporary welding jobs. His job is to sound the warning in case of fire and to try to put it out. Make sure you and the fire guard are able to communicate with ease and that sufficient firefighting equipment is readily available. When extinguishing the flame, shut off the acetylene first. This applies to both injector torches and equal pressure torches. Always close the cylinder valve after completion of a job. Open the valves on the torch to release the pressure and then close them again. Reset the regulator. That way, you won't forget to adjust the correct operating pressure when you resume work. Never leave your equipment pressurized, even during a short break. As we've seen, it's relatively easy to avoid accidents when welding and cutting if we just use the proper methods. If we'll listen to the advice in this film and use the safety equipment recommended, the risk for serious accidents will be minimal.